In this example, we're given a polynomial function in factored form and asked to find the y-intercept, the x-intercepts, which could also be referred to as the real zeros or real roots of the polynomial function, and then also asked to describe the end behavior using this notation here. Looking at the given function, we should recognize that it will be a degree 3 polynomial function, and if we want, we can replace f of x with y and write this as y equals x times the quantity x minus 3 times the quantity x plus 5. And now the process to find the intercepts for any function is the same. To find the y-intercept, we set x equal to 0 and solve for y, and to find the x-intercepts, we set y equal to 0 and solve for x. Let's go ahead and do this on the next slide. And again, let's go ahead and use this form of our equation where we replaced f of x with y. So to find the y-intercept, again, we'll set x equal to 0, so that would give us y equals 0 times 0 minus 3 times 0 plus 5. So we have y equals 0 times negative 3 times 5, which of course is 0. So our y-intercept equals 0, which would be the origin. And now to find the x-intercepts, we'll set y equal to 0 and solve for x. So this would give us the equation 0 equals x times the quantity x minus 3 times the quantity x plus 5. Now in order for this product to be 0, either x, the first factor, must equal 0, or the second factor of x minus 3 must equal 0, or the third factor of x plus 5 must equal 0. So solving for x, this one's already solved for x, so we have x equals 0. Solving for x here, we would add 3 to both sides, so we have x equals 3. Subtracting 5 on both sides, we have x equals negative 5. So here, notice how we have 3 x-intercepts. 0, 3, and negative 5. So going back to the previous slide, the y-intercept was 0. As an ordered pair, we could write this as the point 0, 0. And we had 3 x-intercepts. They were 0, 3, and negative 5. As ordered pairs, we could write the x-intercept of 0 as 0, 0. X-intercept of 3 would be the point 3, 0. And the x-intercept of negative 5 would be the point negative 5, 0. And now to describe the end behavior, we want to describe the value of the function, or the y value, as x approaches the left, or as x approaches negative infinity, and as x approaches right, or as x approaches positive infinity. To do this, we will look at the graph of the given function, but we should also recognize that we can determine the end behavior by determining the lead term of the polynomial function. Notice if we multiplied this out, the leading term would be x to the third. So for our function, f of x has a leading term of x cubed, followed by several other terms. We should be able to determine the end behavior by knowing what the graph of the basic function, y equals x cubed, looks like. The graph wouldn't be the same as our function, but the end behavior would be the same. So if we recognize that y equals x cubed looks something like this, we could use this function to determine our end behavior. Notice as x approaches the right, or as x approaches positive infinity, the function goes up without bound, and therefore y, or f of x, approaches positive infinity. And as x approaches the left, or x approaches negative infinity, the function values go down without bound, and therefore y, or f of x, approaches negative infinity. So this would be our end behavior, but let's go ahead and verify it using the given function in our graphing calculator. So let's go ahead and press y equals, clear out any old function, and type in our new function. We have x times the quantity x minus 3 times the quantity x plus 5. Let's go ahead and press graph. Again, notice how the graph does not resemble the basic function y equals x cubed, but the end behavior is the same. Let's go ahead and adjust the window to get a better view. Let's increase the y max and decrease the y min. So I'm going to change the y min to, let's say, negative 40, and the y max to 60. So notice how as we approach the right, the graph is still increasing without bound, and therefore as x approaches positive infinity, y is approaching positive infinity. As we move to the left, or as x approaches negative infinity, the graph is going down without bound, and therefore y, or f of x, is approaching negative infinity. So this graph does verify our end behavior. As x approaches positive infinity, f of x approaches positive infinity, and as x approaches negative infinity, f of x approaches negative infinity. I hope you found this explanation helpful.